according to a chemist known as Van Arrhenius, an acid is a substance that when dissolved in water produces hydrogen ion as the only positively charged ion. That is according to Arrhenius, and it is called Arrhenius' definition of an acid. This is evidenced in reactions of acids and other substances. Now, what Arrhenius is trying to tell us is that when we have a dilute acid such as hydrochloric acid, it ionizes to give hydrogen ions and chloride ions. From these ions, we are able to tell there is a cation and an ion. The cation is the positively charged ion, which from this ionization we only have a hydrogen ion. Therefore, hydrochloric acid is an Arrhenius acid. We can also have dilute sulfuric 6 acid. It ionizes in water, that is when dissolved in water, it ionizes to produce 2 hydrogen ions and 1 sulfate ion. Again, we have 2 ions produced from that given a dilute acid, that is hydrogen and sulfate, of which hydrogen ion is the only positive ion, meaning sulfuric 6 acid is an Arrhenius acid. Now, let us look at some of the reaction that will try to evidence that indeed an acid is a substance which ionizes to give hydrogen ion as the only positively charged ion. And the first case, we want to have the reaction between sodium hydroxide plus hydrochloric acid, the so-called neutralization reaction. So that gives sodium chloride plus water. Now, the equation is self-balanced. Let's try to write the ionic equation, that is sodium ion plus hydroxyl ion plus the acid will give hydrogen ion and chloride ion, forming, again, in the product we have sodium ion plus chloride ion. Then water does not ionize, and that's why we have water just in liquid state. To cancel out spectator ions, we have sodium, sodium, chloride, chloride, and that gives hydrogen ion plus hydroxyl ion, forming water. Now, it is true that water is formed when hydrogen ions present in the aqueous solution of the acid react with the hydroxyl ion according to the equation as shown above. Now, we have said that the two substances, that is, the acid and the base, react to give salt and water. And from there, we can see both salt and water are neutral substances. And that's why the type of reaction is known as neutralization, as shown below. Now, this sodium ion gives sodium hydroxide gives hydroxyl ion, hydrochloric acid gives hydrogen ion. The two combine to give us water. And of course, chloride and sodium also gives the other neutral substance, which is sodium chloride. Now, we have looked at that first case of neutralization. Let us also consider when now magnesium carbonate is reacted with magnesium carbonate reacted with what we call an acid, hydrochloric acid. And that gives magnesium chloride, carbon 4 oxide, and water. Ionic equation finally will have two hydrogen ions plus a carbonate ion, and that gives carbon 4 oxide gas plus water. From this reaction, it is clear that when hydrogen ions present in aqueous solution of the acid, it gives carbon 4 oxide and water after reacting with the carbonate ion. And we have seen that in the reaction between magnesium carbonate and hydrochloric acid. So different acids ionize in solution. For example, an acid like ethanoic acid, which is an organic acid, also ionizes in solution to give hydrogen ion and ethanoate ion. So it releases hydrogen ion as the only positively charged ion. Therefore, it is also called an Arrhenius acid. Let's look at the second definition of an acid, and that is according to Bronsted-Lowry, the so-called Bronsted-Lowry definition. According to Bronsted-Lowry, an acid is a proton donor. E.g., in the reaction between water and hydrogen chloride gas, or simply and hydrochloric acid, we are able to form, we can use hydrogen chloride so that we don't show much to do with dilution. That gives hydroxonium ion and chloride ions. Now that is water. Oxygen bonded to 2 hydrogen. Then we have the lone pairs. Then the acid donates a proton, and that now gives hydroxonium ion. So we'll have the existing ones, that is proton, another, then the hydrogen ion donated by hydrochloric acid is attached there, and then that is now the hydroxonium ion plus chloride ion. Now, this is the proton donor. and therefore called Bronsted Lowry acid. It donates proton to that water, and from there we are able to have formation of hydroxonium ion. Another example, we can have methylamine also reacting with methylamine like CH3NH2 reacting with water, and that gives CH3NH3 with the charge plus hydroxyl ion. Now again, this one donates a proton, and therefore this is what we call Bronsted Lowry acid, simply proton donor. And you can see this now has more hydrogen ion. Finally, in the same Bronsted Lowry, you can have ammonia gas reacting with water, and that forms ammonium ion plus hydroxyl ion, which is simply ammonia hydrogen, hydrogen. So that is ammonia bonded well. Then water donates a proton, and that forms ammonium ion. That is the existing hydrogen, another existing hydrogen, another existing hydrogen. Then there is a lone pair, so the new hydrogen is accepted there. Then this is charged plus hydroxyl ion. So that is how water again behaves like a Bronsted Lowry acid. So in that case again, water is reacting as an acid. So that is all about the two definitions of an acid. We'll look at strength. That is first based on universal indicator, by use of universal indicator. Then we'll also look at the effect of acids, the effect of electric current on acids, and that we can use to tell which given acid is stronger than the other by simply trying to focus so much on the electrical conductivity of acids. Strong acids are the ones that ionizes or dissociates completely. They're the ones that dissociate completely in water, simply to produce many hydrogen ion. Example, we have hydrochloric acid, which ionizes completely to give hydrogen ion and chloride ion. It is giving hydrogen direct, so therefore it is known as a strong acid. Another example, nitric 5 acid, which also ionizes to give hydrogen ion and nitrate ion. Sulfuric 6 acid, gives 2 hydrogen ions and a sulfate ion. We have seen all the three mentioned acids are strong acids because they are able to ionize completely to give hydrogen ion when in water, and they are giving many hydrogen ions. Now, weak acids dissociate partially to produce few hydrogen ions. Dissociate partially to produce few hydrogen ions. E.g., we have a good example is what we had talked about, that is methanoic acid, which dissociates to give hydrogen ion and ethanoate ion, and you can see that one can still dissociate further. What is formed as the second product can still dissociate further. That's why we are saying it is partial dissociation. We also have the well-known weak carbonic acid. Another example is weak carbonic acid that dissociates partially to give hydrogen ion and hydrogen carbonate ion, meaning the hydrogen carbonate ion formed can still dissociate further, and we are getting few hydrogen ions from there, therefore known as a weak acid. So, strong acids dissociate completely in aqueous solution, while weak acids dissociate partially, and we've seen that in our examples. To give hydrogen ions that are few in number, and they do so in aqueous solution. Now, if you now check on the conductivity of these acids, you realize that strong acids have higher electrical conductivity. Since they have many mobile ions. We have mentioned there that they ionize to give many hydrogen ions. So, the number of mobile ions that they give in solution are higher compared to the ones for weak acids. And that's why when hydrochloric acid is used, that is, when we test the conductivity of hydrochloric acid, then we use this acid as the electrolyte. It is clear that it causes a bigger deflection of the ammeter, since conductivity is dependent on the amount of ions present. And that is confirmed clearly by the fact that hydrochloric acid, which is a strong acid, has a high number of hydrogen ions, and that is why it has that higher electrical conductivity. Well, weak acids have lower electrical conductivity. Reason being that they have few number of mobile ions. And we have seen that from the fact that they have few hydrogen ions. So the number of mobile ions when in solution is lower than that in strong acids. And other examples of weak acids include methanoic acid and ethanedioic acid. Generally, all organic acids are weak acids because they ionize partially when in solution. Now, we have looked at keenly the ionization, and from that we have tried to check on the electrical conductivity. Let us now again try to relate this strength by looking at the effect on the universal indicator. Use of now universal indicator to tell the strength of acids and bases. To start with acids that we are still discussing, we know that acids have a pH value below 7. Acids have pH value below 7, where strong acids have lower pH value since they have high number of hydrogen ions. High number of hydrogen ions. And that's why you get that the pH value of an acid like hydrochloric acid is below 4. It has, pH is all about potential hydrogen. So, if we talk about the pH value, then it is clear mathematically that the higher the number of hydrogen ions, the lower the pH value. From the log concept, we are able to tell that the higher the number of hydrogen ions, the lower the pH value. And that's why strong acids have lower pH value and is normally between 0 and 4. Similarly, weak acids have higher pH value because of few number of hydrogen ions. So, the lower the number of hydrogen ions, the higher the pH value. And because of this few, their pH value ranges between 4.1 to 7. Simply 4 to 7. That is for weak acids such as methanoic acid. Now, NB. Please note that a weak acid does not necessarily mean dilute or strong acid. That does not necessarily mean dilute acid. Don't confuse the two. And strong acid does not mean concentrated acid. Remember, concentrated acid simply is determined by the number of moles in a given volume of that acid. That is how we tell concentration of the acid. It has nothing to do with the number of hydrogen ions. Now, as students, I want us to look at that story in a very civilized way. Let us say there are more hydrogen ions. The more hydrogen ions has nothing to do with number of moles of the acid in a given volume of that acid. But that number of hydrogen ions is all about the strength of that acid. And that's why we are saying when there are many hydrogen ions, then the acid is strong. And when there are higher moles of the acid in a given volume, then the acid is concentrated. I wanted to join those together so that we get the difference between a concentrated acid and a strong acid. Similarly, dilute acid and a weak acid. This therefore means that ethanoic acid, which is known to be a weak acid from what we have learned today, can be said to be concentrated. That is, when there are higher moles of the acid in a given volume. So it is said to be concentrated. Again, hydrochloric acid, that is well known to be a strong acid, can be said to be a dilute acid. That is, by adding more solvent to it, you are making it dilute. So it is not now concentrated, but still remains a strong acid because of many hydrogen ions. That is all about strength of acids. Today, let's talk about bases. Remember, the topic is acids, bases, and salts. Just like the two definitions of acids, bases are also defined differently by two different chemists. According to Vast Arrhenius, a base is simply a substance that dissolves in water to produce hydroxyl ion as the only negative ion. And a good example of a base is sodium hydroxide. So when sodium hydroxide ionizes, it gives sodium ion, which is a positive ion, and hydroxyl ion. So that is the negative ion, and according to Arrhenius, this one is a base. So it's therefore called Arrhenius base. Potassium hydroxide behave in a similar manner. Potassium hydroxide in solution will dissociate to give potassium ion, that is positive, plus hydroxyl ion. So that is the only negative ion, and therefore potassium hydroxide is also an Arrhenius base. Another good example that we can talk about is calcium hydroxide. This ionizes to give calcium ion and 2 hydroxyl ion. So that is also said to be a base, and according to Arrhenius, it dissociates in water to produce hydroxide ion as the only negatively charged ion, and the resulting solution is able to turn red litmus paper blue, as the blue one remains the same, that is remaining blue. Let us look at the definition of a base according to Bronsted-Lowry. But before that, we want to look at some reactions where we have our bases showing the evidence of the production of hydroxyl ion, and that is where we have sodium hydroxide plus hydrochloric acid to form sodium chloride and water. That is ionic equation: hydrogen ion from the acid plus hydroxyl ion from the base, and that gives water, therefore called neutralization reaction. Now, sodium hydroxide is an Arrhenius base, reason being that it dissolves in water to give hydroxyl ion as the only negatively charged ion. Similarly, hydrochloric acid is an areneous acid because it gives hydrogen ion as the only positively charged ion. Another equation can be between copper 2 oxide and sulfuric 6 acid. Or we can use copper 2 hydroxide sulfuric 6 acid, and that gives copper 2 sulfate plus water. Another neutralization reaction where we have hydroxyl ion combining with hydrogen ion to give us water. To balance the equation, we have hydrogen 4, so that should be 4. Then the equation is balanced. Liquid, aqueous, aqueous, solid. Let's look at another definition of a base, and that is according to Bronsted-Lowry. According to Bronsted-Lowry, he defined a base as a proton acceptor. What accepts the proton? What receives that proton? Now, an example, we have ammonia plus water to form ammonium ion plus hydroxyl ion. And such equations are normally said to be reversible. Or simply at state of balance. So we have that. That is aqueous, aqueous gas. Now, ammonia that is hydrogen, hydrogen, that is ammonia plus the proton, and that gives ammonium ion. That is the newly formed bond. Then these are the ones that were existing before. that is ammonium ion, and then it gives that out. So there is no need of including this because we are having just ammonia gas and hydrogen ion. Now, this ammonia has a lone pair of electron. It is able to accept the hydrogen ion to form ammonium ion. So this is what we call Bronsted-Lowry base. It accepts the proton. So water is the Bronsted-Lowry acid and ammonia is the Bronsted-Lowry base. Another example, methylamine. We can have CH3NH2 reacting with water, and that gives CH3NH3 with the charge plus hydroxyl ion. Now, this one is able to accept a proton that is from water, and that forms an extra hydrogen there, meaning it is the proton acceptor, and therefore called Bronsted-Lowry base. Simply a proton acceptor. So that is all about the two definitions of a base. Lesson, we talked about the definition of bases based on Arrhenius definition and Bronsted-Lowry, where we said, according to Arrhenius, a base is simply a substance which, when dissolved in water, ionizes to give hydroxyl ion as the only negatively charged ion. Similarly, according to Bronsted-Lowry, a base is a proton acceptor, and out of that we were able to tell that ammonia is a Bronsted-Lowry base. You know, when we were talking about Form 3 chemistry, we said that ammonia is able to turn moist red litmus paper blue, showing its basic property. So it is this topic that now categorizes for us well how ammonia is treated as a base, because it is this topic that tells that ammonia is a proton acceptor, which according to Bronsted-Lowry becomes a base. Therefore, ammonia gas is fully basic in nature. In this lesson today, let us now discuss the strength of these bases. Which ones are stronger than the other? So that is, a strong base is one which dissociates completely in water, completely in water, to produce many hydroxide ion. And a good example is potassium hydroxide, which ionizes to give potassium ion and hydroxyl ion, the so-called hydroxide ion. Another one is sodium ion and that ionizes to give sodium ion and hydroxide ion completely to give the hydroxide ion. Weak bases dissociate in water to produce few hydrogen ions, and they dissociate to give indeed few hydroxyl ion. Dissociate in water to give few hydroxyl ions. A good example is ammonia solution, which dissociates to give ammonium ion and hydroxyl ion. So this is known as a weak base. Just like we talked about the strength of the acids, we are able to use the same to tell which base is stronger than the other and why. And we want to start that by looking at the behavior when we use universal indicator. So the first one is universal indicator. So with the universal indicator, strong bases have higher pH values. They have higher pH values, and that is between 10 to 14. Reason being that they have many hydroxyl ion and few hydrogen ions. Remember, pH is about potential hydrogen. So when the number of hydrogen ions are very few, then the pH value goes higher. So they have many hydroxyl ion, and that is why their pH values is high. So the higher the number of hydroxide ions, the higher the pH value, and that is why sodium hydroxide, which is a strong base, has a pH value above 10. Weak bases have slightly lower pH values, that is between 7 to 10. For these ones, they have fewer hydroxide ions compared to the strong bases, and that is why their pH values are lower, and that is between 7 and 10. So if we consider the examples we have mentioned, that is ammonia and sodium hydroxide, then sodium hydroxide has a higher pH value, and then ammonia solution has a lower pH value because it has fewer hydroxide ion compared to sodium hydroxide solution. Another reasoning can be based on electrical conductivity. Still, to explain the strength of bases, sodium hydroxide solution has many hydroxide ions than ammonia, and because of that, its conductivity is higher. So strong bases have higher electrical conductivity. And that is because of many ions, many mobile ions. They dissociate completely or ionize completely to give sodium ions, for example, and hydroxyl ion, and that will enable conductivity. Weak bases have lower electrical conductivity. And reason being that they have few mobile ions. few hydroxyl ions, just like we have said, and that is what is responsible for their low conductivity compared to strong bases. That is all about the strength of bases. Effect of solvent on a solute. We want to discuss this by first looking at an experiment, and this is the experimental procedure. Dissolve hydrogen chloride gas in water. Divide the solution into 3 portions. To the first portion, place magnesium ribbon. Then test the second portion with the litmus paper. To the third portion, add magnesium carbonate. Then record your observation. Repeat this experiment by dissolving hydrogen chloride gas in methyl benzene, which is an organic solvent. Then also record your observations. Observations and explanations. Let's look at observations and explanations. A solution of hydrogen chloride in water display acidic property. By turning blue litmus paper red, Another one, reacting with magnesium or any metal to form magnesium chloride and hydrogen gas. Also reacting with magnesium carbonate to form magnesium chloride, carbon 4 oxide, and water. And during that, it produces effervescence or simply bubbles. It's also capable of reacting with bases to form salt and water. Can conduct electric current, and during that will produce bright light. Reason being that the hydrochloric acid formed is able to ionize fully to give hydrogen ions and chloride ions. Now, what happens there is that water is a polar solvent, and that polar solvent has negative and positive charges. So let's check on that. So when it is dissolved in water, which has a polar solvent, and you can see it has partial charges. This water molecule consists of one oxygen atom and two hydrogen atoms. Since the oxygen has a higher ability to attract bond electrons compared to hydrogen, meaning oxygen is more electronegative. The bond pairs of electrons are closer to oxygen atom in the water molecule, leading to the oxygen atom developing a partial negative charge, while the hydrogen will now develop a partial positive charge. We have said oxygen is more electronegative. It has high ability to attract a bonded pair of electrons. And a molecule which behaves as if it is negatively charged in one end and positively charged in one end is said to be polar. And that's why water is a polar solvent. We have said a molecule which behaves as if it is negatively charged in one end and positively charged in the opposite end is said to be polar. Therefore, water qualifies to be called a polar solvent. Remember, hydrogen chloride is also polar. It has hydrogen ion and chloride ion, negative and positive on different ends. And this is because chlorine has a higher ability to attract bond electrons compared to hydrogen. The chlorine end of the molecule, therefore, will develop a partial negative charge as the hydrogen end develops a positive charge. Meaning, now water has negative and positive ends. Hydrogen chloride also has negative end and positive end. Now, when this hydrogen chloride is dissolved in water, different water molecules attract both ends of hydrogen molecules, causing it to dissociate. You can see that attack and that attack, and that make it to dissociate. This implies that the covalent bond is broken in such a way that the shared pair of electrons are left with the chlorine atom, thus creating negatively charged chloride ion and positively charged hydrogen ion. From that dissociation, this is what we have. After that solubility, the formed hydrochloric or simply hydrogen chloride gas dissolves in water to give hydrogen ion and chloride ion. And the presence of these hydrogen ions is what brings acidity. So that makes this one acidic. And therefore, this same presence of hydrogen ion is what will now make it to turn blue litmus paper red, react with magnesium carbonate to liberate carbon 4 oxide. It is this same thing that will make it to react with magnesium to liberate hydrogen gas, and it is this same presence of ions after dissociation that will enable electrical conductivity. Now, it is clear that the hydrogen ions will now be able to react with magnesium carbonate, and that gives magnesium ion carbon 4 oxide and water. So the carbon 4 oxide and water is just formed between from the reaction between the acid and the carbonate due to presence of hydrogen ion, and by having that there, our equation is balanced. Now, the story is that the hydrogen chloride gas, it is able to ionize in water, and we have explained that because of simply polarity of water. Being that hydrogen chloride is polar, water is also polar, hydrogen chloride is able to dissolve and ionize to give the mobile ions that will enable conductivity, will also enable production of effervescence. That is when it is reacted with either magnesium or magnesium carbonate. What happens to the case of methyl benzene? Methyl benzene is nonpolar solvent. And when hydrogen chloride gas is dissolved in methyl benzene, its molecules do not dissociate. Well, it will dissolve because both of them are are covalent in nature. So because of the covalence nature, it will just dissolve. But remember, its molecules, that is the molecule of hydrogen chloride, does not dissociate into hydrogen ion and chloride ion. And therefore, no hydrogen ion is present. No present hydrogen ion. And because of that, there is no effect on litmus paper, especially the blue that should turn red, does not react with both magnesium and magnesium carbonate. So there is no production of effervescence. So if we test for the electrical conductivity, then the bulb will remain dim because methyl benzene does not allow hydrogen chloride gas to ionize to give mobile ions. And because of the absence of mobile ions, the result we have mentioned above will take place. Similarly, we can also look at the behavior using a base. Similarly, ammonia gas only shows basic property in water, and reason is that it is able to ionize to give ammonium ion and hydroxyl ion, and the presence of hydroxyl ion will be responsible for the basic property. In methyl benzene, it does not show basic property. Because ammonia remains a molecule. Here, ammonia remains a molecule. So it will not be able to react as a base. It does not produce the hydroxyl ion and fully remains as a molecule, hence no basic property. That is all about the effect of a solvent on a solute. Lesson, we talked about the effect of solvent on a solute, where we investigated the effect of water and methyl benzene on acids and bases. We realized that hydrogen chloride gas is able to ionize in water because of the non-polarity of water and the gas. And that enables the hydrogen chloride gas to show acidic property in water. The same does not take place in methylbenzene, a reason being that hydrogen chloride remain a molecule in methylbenzene, which is a non-polar solvent, meaning it does not ionize to give hydrogen ions responsible for the acidic property. Similarly, ammonia as a base is able to ionize in water to give the hydroxyl ion that is able that enables it to show the basic property. And that does not happen in the case of methylbenzene because the ammonia molecule will simply remain as a molecule and will not give the hydroxyl ions, hence no basic property. Today, in this lesson, let us talk about amphoteric oxides and hydroxides. What are these amphoteric oxides and hydroxides? Now, these are oxides and hydroxides exhibiting both acidic and basic properties. i.e., they react as both acids and bases. To form salt and water. Let's look at examples of amphoteric oxides and hydroxides. To start with the oxides, they include zinc oxide, lead 2 oxide, and finally we have aluminium oxide. That is the formula of aluminium oxide. That is lead 2 oxide, and that is zinc oxide. The hydroxides include same metals, so that is zinc hydroxide, aluminium hydroxide, and lead 2 hydroxide. Let us now look at the reactions between these oxide, how they react as an acid and a base. And the first one, we want to look at the reaction of lead 2 oxide as a base. That is lead 2 oxide, which is a base, plus nitric 5 acid dilute to form lead 2 nitrate and water, simply forming salt and water. To balance the equation, we have there 2, and therefore our equation is fully balanced. Let's look at lead 2 oxide as an acid. It will be lead 2 oxide solid plus sodium hydroxide as a base, and that gives sodium plumette. That is sodium plumette plus water. Of course, salt plus water. This is what we call sodium plumette plus water. The next one, we want to look at zinc oxide as a base and acid. That is number 2. Zinc oxide as a base. That is zinc oxide plus an acid. We can work with the same acid or change the acid and still have the same thing. So that is sulfuric 6 acid will give zinc sulfate aqueous plus water. The state symbols important. The equation is self-balanced. Zinc oxide as an acid will give zinc oxide plus sodium hydroxide. That gives sodium zincate. That is what we call sodium zincate. Plus water. That is the first 2 reactions involving zinc oxide and lead 2 oxide. Let's look at the one between aluminium oxide. We start by as a base. As a base, it reacts with nitric acid, aluminium oxide plus nitric 5 acid to form aluminium nitrate plus water, that is 2, 6, and the equation is balanced. You can have 3 there, yes. So next is aluminium oxide as an acid, and that gives aluminium oxide plus sodium hydroxide, which is a base, forming sodium aluminate, this is sodium aluminate plus water. In this reaction, metal oxides are reacting as bases and also as acids. In the case where they're reacting as acids, we have formation of colorless solution such as sodium zincate for the case of zinc oxide. We have sodium plumbate for the case of lead 2 oxide, and also sodium aluminate, that is when we use aluminium oxide. The hydroxides will also react in a similar manner, and they are going to give different colorless solution when they react with sodium hydroxide. And for the case where they react as bases, they also give respective metal salt and water. That is all about amphoteric oxides and hydroxides. But you have to know that hydroxides react in a similar manner that is as oxides. So we don't need to write other equations for the hydroxides. They will follow the same trend except the case of balancing due to difference in formulae. So that is the end of our lesson. Hello and welcome to this lesson. Let's talk about salts. recall in Form 2 chemistry, we discussed the topic salts, where we look at so much to do with the solubility of salts and how to prepare different salts by simply studying the different methods that are used to prepare salts. Let us start this lesson by defining the word salt. So salt is simply an ionic compound formed when a cation removed from a base combines with an ion derived from the acid. So for example, if we have hydrochloric acid reacting with sodium hydroxide, then the cation from the base is sodium ion combining with the anion from the acid, and the two will give sodium chloride salt. When an acid reacts with a base, hydrogen ion in a base hydrogen ion is or are fully or partially replaced by metal ion. So the hydrogen ion in an acid get partially or wholly replaced by a metal ion, which can either be from a base or simply even a metal. And this also can be ammonium radical. Now, we can have an acid such as sulfuric 6 acid reacting with ammonium sulfate. Now, or sulfuric 6 acid and ammonium hydroxide. So what will happen? The ammonium ion from the base, that is ammonium hydroxide, will replace the hydrogen ion in the acid, so that the sulfate ion combines with ammonium ion to form ammonium sulfate salt. So the salt in question is ammonium sulfate, then finally plus water. Let's discuss precipitation reactions. A precipitate is an insoluble solid that separates out from a solution during chemical reaction. From a solution during chemical reaction. For example, when lead 2 nitrate is added to sodium sulfate, of course sodium sulfate solution, a white solid is observed. This is the so-called white precipitate. And this is due to the equation below. So equation for that formation is as follows. Lead 2 nitrate aqueous reacts with sodium sulfate, also a soluble salt, to give a precipitate, and that is lead 2 sulfate plus sodium nitrate. Now this is the white precipitate. To balance the equation, we have there 2. Then our equation is just fully balanced. So the white solid that is observed during this reaction, we have said, is due to formation of lead 2 sulfate. Let's have a summary of some precipitation reactions. Summary of precipitation reactions. So we want to have sort of a table for the summary of the reactions. First column, simply a summary of precipitation reactions. Sodium chloride, sodium carbonate will be there. Then we'll have sodium sulfate. Then that is a colon. So this is the table that you want to use for the summary. First column, that is for another cation, cation, that is for another cation. Now the first one, we have the first column, solution containing then sodium chloride, sodium carbonate, sodium sulfate, and finally we have sodium sulfite. The first one is lead-2 ion, barium ion, magnesium ion, calcium, zinc, and copper 2 ions. When a solution containing lead-2 ion, for example lead-2 nitrate, is reacted with sodium chloride, there is formation of a white precipitate. And the white precipitate is of lead-2 chloride. It also forms a white precipitate of lead-2 carbonate with sodium carbonate. Same to white precipitate with sodium sulfate, and that is of lead-2 sulfate. The last one also gives a white precipitate. barium, iron, and sodium chloride will give barium chloride, which is a colorless solution. But under observation, we write no precipitate. That is no precipitate. With sodium carbonate, it forms a white precipitate. Sodium sulfate, that one also forms white precipitate of barium sulfate. And finally, white precipitate of barium sulfite. Magnesium. Magnesium chloride is soluble, so no white precipitate. Magnesium carbonate is insoluble, that is white precipitate. Magnesium sulfate is soluble, so no precipitate. Magnesium sulfite is soluble. But that depends fully on what we are using. So the observation will rest on the experiment, and that is forming no precipitate. Calcium chloride is soluble, no precipitate. Calcium carbonate precipitate, so that is white precipitate. The next is calcium sulfate, slightly soluble, so that is precipitate. White precipitate. Then calcium sulfite, that is also white precipitate. Zinc, iron. Zinc chloride is colorless, so no white precipitate, simply no precipitate. Zinc carbonate is a white precipitate. Zinc sulfate, no precipitate, because that is soluble salt. Zinc sulfite is a white precipitate. Copper 2 ion. Copper 2 chloride is colorless, so no precipitate. Copper 2 carbonate, white precipitate. Copper 2 sulfate, no precipitate. And finally, copper 2 sulfite will give a yellow precipitate. So when it reacts with sodium sulfite, it gives a precipitate. So we can see from the above that soluble salts can be used to precipitate the insoluble salts. And we have seen to precipitate other soluble salts, and we have seen in our table. Now, that is all about precipitation reactions aware, we have realized how exchange of anions take place, and that results into formation of precipitates. However, there are some cases where there is formation of a colorless solution. Let's talk about the effect of sodium hydroxide solution on different cations, or simply ions. And the cations we want to study include magnesium ion, barium ion, zinc ion, aluminium ion, lead 2 ion, copper 2 ion, iron 2, and iron 3. Let us start by looking at addition of sodium hydroxide solution on magnesium ion. Observation. And a few drops a white precipitate is formed. When you add few drops of sodium hydroxide solution on a solution containing magnesium ion, we are forming a white precipitate. The observation is simply white precipitate. And this white precipitate is due to formation of magnesium hydroxide. Now, the magnesium ion reacts with the hydroxyl ion from sodium hydroxide to form magnesium hydroxide. So that is solid. In excess of sodium hydroxide, the precipitate remains insoluble. Now, when we add excess sodium hydroxide solution, the white precipitate remains insoluble. So, we'll still have insoluble magnesium hydroxide. So this is still magnesium hydroxide. The second one, let us look at addition on barium ion solution, maybe barium chloride, which is a solution containing barium ion. So we'll have few drops, or simply dropwise, and then excess. So that is dropwise, and then we'll have excess. So dropwise, the observation is white precipitate is observed. Or simply, white precipitate is formed. In excess, the white precipitate remains insoluble. Let us now see the cases of our white precipitate under limited supply and excess. So that is when you do the dropwise white precipitate, then excess of sodium hydroxide solution, we still have formation of a white precipitate which remains insoluble. So the precipitate remains insoluble. Now the equation for the reaction is as follows. It is barium ion reacting with hydroxyl ion to form barium hydroxide, which is solid, and this is the white precipitate, which remains insoluble. Now, those are our two. That should be two for us to have the equation well balanced. There has to be 2 as a coefficient of hydroxyl, and that is what we have said is a white precipitate formed. So to balance this equation as well, we must have 2 there. Number 3, let's have addition of sodium hydroxide solution on copper 2 ion. Maybe copper 2 nitrate having copper 2 ion. So that will be few drops or dropwise of sodium hydroxide. So this side will have dropwise, and then we have excess. So dropwise observation, we have blue precipitate, is formed. Excess blue precipitate remains insoluble. So that is due to formation of copper 2 hydroxide, where we have said we'll have underdropwise blue precipitate, and even in excess the blue precipitate remains insoluble. So that is the blue precipitate with copper, and under excess, that is when you add excess sodium hydroxide solution, we will still have the blue precipitate being insoluble. The equation for this reaction is as follows. We have copper 2 ion reacting with the hydroxyl ion from the sodium hydroxide to form copper 2 hydroxide, which is in solid state. The next one is ion 2, that is number 4. Ion 2 ion, dropwise, then we'll have excess. So dropwise of sodium hydroxide solution, we are forming green precipitate. Green precipitate is formed. That is observation, dropwise, excess, green precipitate remain insoluble. So it gives a green precipitate that does not dissolve in excess, meaning it is due to formation of ion 2 hydroxide that remain the same even in excess. So that is limited supply, where we are able to see there is the green precipitate with ion 2, and in excess the green precipitate remain insoluble. We now have excess of that. Our green precipitate is there insoluble, and this is due to the reaction between ion to ion with hydroxyl ion from sodium hydroxide solution to form ion 2 hydroxide, which is in solid state. Our next one is ion 3, that is number 5. Ion 3 ion. So we have dropwise and excess. Under dropwise, there is formation of brown precipitate. So brown precipitate is formed. Excess, brown precipitate remain insoluble. So this brown precipitate is due to formation of ion 3 hydroxide, which on addition of more drops of sodium hydroxide solution does not dissolve, but instead remain insoluble as shown in this given test tube. So this is when it is few drops, and that is excess. These few drops, even if you leave it for long, it will still remain insoluble. The reaction there is that ion 3 ion reacts with the hydroxyl ion to form ion 3 hydroxide, which is the brown precipitate. The next one is zinc ion. Zinc ion in dropwise will give a white precipitate. So a white precipitate is formed. In excess, white precipitate dissolves to form colorless solution. So that is due to formation of a complex ion. Let's look at case of few drops, where we have said that will give a white precipitate, but in an excess The white precipitate dissolves to form a colorless solution. So in few drops, that is the white precipitate. You can have another different test tube, but same white precipitate. Then in excess, the white precipitate dissolves to form a colorless solution. And we have said the colorless solution is simply due to formation of a complex. So two reactions will take place here. The first one is for the white precipitate, where we'll have zinc ion reacting with hydroxyl ion to form zinc hydroxide. And this is the white precipitate. Then in the colorless solution, the white precipitate formed reacts with more hydroxyl ion from excess sodium hydroxide to form a colorless solution. So that is the complex ion formed that is now colorless. Zinc tetrahydroxide ion, as you can see in the equation. Number 7 is what we call aluminium ion. Dropwise, and then we have excess. Aluminium dropwise, there is formation of a white precipitate as the observation. White precipitate is formed. In excess, the white precipitate dissolve to form a colorless solution. Let us have a check on the white precipitate that is formed, and that is due to formation of aluminium hydroxide. And this aluminium hydroxide, on excess addition of hydroxyl ion, it will give a colorless solution, and that is due to formation of a complex. So that is the colorless solution. So the reactions which take place here include the first one, aluminium ion, maybe from aluminium nitrate, reacting with the hydroxyl ion from sodium hydroxide to give aluminium hydroxide, which is the solid substance. Then this aluminium hydroxide will react with the extra hydroxyl ion to form a complex, and this is the complex that we get from that given reaction. So this is a colorless solution. Finally, the last one, number 8, we have lead 2 ion under dropwise and excess. Observation under dropwise: a white precipitate is observed or formed. Excess: the white precipitate dissolve to form a colorless solution. In the dropwise, we have said we have a white precipitate of lead 2 hydroxide. Then in excess, the precipitate dissolves to form a colorless solution. So that is white precipitate, and this is our white precipitate of lead 2 hydroxide. Then in excess, it will form a complex, and that is why we are getting colorless solution. So this is the complex ion formed. So the reactions as follows: lead ion reacts with hydroxyl ion to form lead 2 hydroxide, which is the white precipitate. Then this white precipitate reacts with excess hydroxyl ion to form a complex ion, and that is what is responsible for the colorless solution. So this is colorless. So it is clear that the amphoteric oxides, aluminium or simply amphoteric hydroxides, that is aluminium, zinc, and lead, are able to give what we call the colorless solution with excess sodium hydroxide. Now, I want us to recall the observations that we talked about when we were learning the addition of ammonia solution. We said that is only zinc ion and copper 2 ion that are able to form complexes, and for that reason they give solutions in excess addition of ammonia solution. In this case today, we have realized that aluminium ion zinc ion and lead ion with excess sodium hydroxide, they give colorless solutions. They simply give solution due to formation of complexes. So it is this complex ion formation that enables a solution to be realized on excess addition of either sodium hydroxide solution or ammonia solution. Now, from this chemistry, we can therefore conclude that only zinc ion, or simply only zinc hydroxide, is able to dissolve in excess. Only zinc hydroxide dissolve in both excess ammonia solution and sodium hydroxide solution. Very important. That is why when you do for ammonia, you get zinc ion, few drops, it forms white precipitate, then excess gives colorless solution. And the same story happens when we now use a sodium hydroxide solution. In complex ions, the ammonia molecule and the hydroxyl group form a dative bond with the metal ions. And these complex ions are important in industry and also in biology. Like chlorophyll and hemoglobin are already complex ions. Like if you check the hemoglobin, it is a complex ion, and it helps in the blood oxygen transportation in the body in the form of oxyhemoglobin. That is all about the effect of sodium hydroxide solution on different metal ions. Let's talk about solubility. In book 2, we looked at soluble and insoluble salts. where we mentioned some of the examples of salts that dissolve in water, such as the salts of sodium, potassium, and ammonia, and even examples of salts that are not able to dissolve in water. In this lesson, we want to discuss simply the solubility. And solubility of a solid is the mass of the solute in grams that can dissolve in 100 grams of water to make a saturated solution at a stated temperature. Saturated solution at a given temperature. And remember, a saturated solution is one that cannot dissolve any more solute. Saturated solution is one that cannot dissolve any more solute at a given temperature. Like if a given solution is said to be saturated, then addition of extra solute will simply settle at the bottom of the apparatus because it cannot hold any more solute. When the temperature of the solution is changed, the amount of solute required to form a saturated solution also changes. Let's look at an experiment. To determine solubility of potassium nitrate in water at room temperature. We want to investigate solubility of potassium nitrate in water at room temperature. Procedure. Weigh an evaporating dish with a watch glass that fits over it. Measure 20 cubic centimeters of a saturated solution of potassium nitrate. Saturated potassium nitrate solution. Next, transfer it into the weighed dish, then record the temperature of the solution. Record temperature of the solution. Weigh the dish together with the saturated solution and the watch glass. Heat the solution gently to dryness. Because when you heat with a lot of heat, when you use a lot of heat, it may decompose the potassium nitrate. Then allow it to cool and reweigh and record the mass. Thereafter, we have the questions to answer. Question 1. Determine the mass of solute and solvent. The second one, determine the mass of solute that dissolves in 100 cubic centimeters of water at that temperature. Solution. It is recorded that temperature of the solution is 15 degrees Celsius. Then mass of dish plus watch glass plus solution is equals to 85 grams. And the mass of dish plus watch glass is equals to 55 grams. And then mass of dish plus watch glass plus solid salt, that is after heating, is 61 grams. Therefore, the mass of saturated solution will be 85 minus 55, and that is 30 grams. Meaning that mass of solute is equals to 61 minus 55, and that gives 6 grams. Mass of solvent will be the 85 minus 55 plus that solute, and that gives 24 grams. From the result, it is clear that 24 grams of solvent, that is water, dissolve 6 grams of solute at a temperature of 15 degrees Celsius. This means that 100 grams of water now will dissolve a what given amount of solute. Now, part 2 of the question will be, if (24 grams of water dissolves 6 grams of solute, then how many grams of solute will 100 grams of water dissolve? Remember, density is mass over volume, meaning mass is density of water times the volume. So that is 100 times 6 over 24, and that gives 24 grams of solute that dissolves in 100 cubic centimeters of water. In 100 cubic centimeters of water. Thus, solubility of this value is 25, if you calculate it well. Therefore, solubility of the salt is equals to 100, will be 25 grams per 100 grams of water at 15 degrees Celsius. Now, the solubility of a solute in a solvent is what we said is the maximum mass of solute required to saturate 100 grams of solvent at a particular temperature. So we have to mention the 100 grams of water and also state the temperature, and that is the full way of writing solubility. Now, if you have calculated the solubility, it has to be put in that form by stating even the temperature. 2 grams of copper 2 sulfate and 50 grams of water were mixed until no more salt could dissolve. The undissolved salt was filtered out washed and dried. It weighed 6 grams. A. Calculate the solubility of copper 2 sulfate at the temperature of the experiment. Part B. Calculate the percentage by mass of the solute in the saturated solution. Solution A. Mass of copper 2 sulfate dissolved is equals to 22 minus 6, that gives 16 grams. Therefore, solubility will be, if 50 grams of water dissolve 16, 100 grams of water will dissolve 100 times 16 all over 50 once, twice, and that is 32 grams per 100 grams of water. Then part B of the question in the solution, percentage by mass is equals to the 32 over the overall mass, that is solvent plus solute, then times 100%. That will give 24.24%. Remember, it is a mass of solute over total mass of solvent plus solute. Then we multiply by 100%. Before we look at the graphical aspect of solubility, let us do another example where we can now use the formula method. Another example, calculate the solubility of salt Q given that 5 grams of the salt form a saturated solution in 40 grams of water at 10 degrees Celsius. Solution. Solubility in formula is equals to 100 grams of water multiplied by mass of solute over mass of solvent given mass of solvent. And this is the formula that you're going to use to calculate different solubility questions. So that means we have 100 times the solubility, the mass of the solute, which is 5, over mass of solvent, that is 40. That is 1 to 8, then that divides 4 to 425, and that is exactly 12.5 grams per 100 grams of water at 10 degrees Celsius, and that is our solubility. Another example. It is normally important to do many examples so that we understand them better. Another example. The solubility of potassium chlorate is 5 grams per 100 grams of water at 50 degrees Celsius. How much of the chlorate form a saturated solution with 5 cubic centimeters of water at the same temperature? Solution. Again, solubility is equals to 100 grams of water times mass of solute all over mass of solvent well. So we have the solubility as 5, then it is mass of the solute that we are looking for. So that will be simply, when we cross multiply, we'll have 100 times 5 over 5, and that gives 0.025 grams. It is a mass of solute. So without multiplying direct, we can have 5 is equals to 100 times Y over mass of solvent, which is 5. And that will give 5 times 5 over 100 to be equals to Y. And finally, that gives Y to be 0.025 grams. Therefore, mass of solute is equals to 0.025, or simply 0.25. Sorry, that should be 0.25. We are dividing by 100. 25 grams. Our last example, we have a case where now we have 22 grams of salt was dissolved in 40 grams of water at 10 degrees Celsius. Calculate the solubility of the salt. Solution. So we have solubility is equals to 100 grams of water times mass of solute divided by mass of solvent. So is solubility we are looking for. So that will be 100 times 22 over 40, and that gives 55. Therefore, solubility, simply that and that, 2, 5, 1, 11. That is how we are getting our 55. Solubility is equals to 55 grams per 100 grams of water at 10 degrees Celsius. So that is all about the solubility calculations. Effect of temperature on solubility, where we'll simply discuss the solubility curves. Let us look at the effect of temperature on solubility of potassium chlorate. And we want to use a data of temperature and solubility. So that is mass of potassium chlorate in grams per 100 grams of water. Then we shall have temperature. A temperature of 88. The mass or rather solubility, is 40. 52, solubility of 20. 38, solubility of 13.3, and 31, solubility of 10. 25, solubility of 8.0. Let us plot the graph of solubility against temperature. So we have the y-axis is solubility, then the x-axis we have temperature. So this is the y-axis. Then we have the x-axis. That is 0, then 10, 20, 30, 40, 50. And this is our y-axis, and this is x-axis. In the x-axis we have this as 20, 40, 60, 80, and then 100. So the first plot is, remember, this is temperature. Then we have solubility, and that is in grams per 100 grams of water. The first plot is solubility, temperature of 88. This is 80. This is 90. So 88 is here. So 88 against 40. That is 88, 40. Then we have 52, 20, 50, then 52 against 20. There is 38, 13.3. This is 38 along the x. 15 is here. So 13.3. Then we also have 3110, 30, then 3110, finally 25:8, the middle, then up to 8, so close to that, then we want to join this to draw our graph on solubility. A smooth curve, and this is for potassium chlorate. Smooth curve of the solubility of potassium chlorate against a temperature. You can see from the graph that increase in temperature results into increase in solubility. Like when the temperature is 80, solubility is higher, and that solubility is 50 degrees Celsius. 50 grams, per 100 grams of water. When the temperature is 60, the solubility is now lower. So this is at 60, this is at 80. You can see from there that the solubility is simply directly proportional to temperature, where temperature increase results into corresponding increase in solubility. Meaning, as the temperature rises, the solubility of potassium chlorate increases, and for most salts, solubility increase with the same rise in temperature. However, the solubility of such salts, such as sodium chloride and calcium sulfate, remain almost constant with the temperature change, while the solubility of salts such as calcium ethanoate decreases with increase in temperature. And you can see that by simply looking at different solubility curves. Let us now have a series of solubility curves that we can use to simply analyze how different salts dissolve in water. So this is the grid we want to use to sketch solubility of different salts. And to sketch solubility of different salts. We have the x-axis as usual, temperature, y-axis is solubility in grams per 100 grams of water. So in the x-axis we can have 10, 20, 30, that as 40, 50, and then 60, and that is in degrees Celsius. In the y-axis we can have other units as well. Ten, 20, 30, 40. Now, for example, for potassium nitrate, the curve will take that shape. For sodium chloride, the curve takes that shape. Potassium chloride, that is potassium chloride. Potassium nitrate, we have seen an increase almost from 0, taking that shape. And calcium sulfate, almost a straight line. So that one is for calcium sulfate. So the first curve, this is for potassium nitrate. These are sketch for potassium chloride. Then this is potassium chloride. And then we also have sodium chloride and calcium sulfate. So these are the sketch of simply for different solubility curves. Let us now look at the last part of these curves, where we want to use our curve to determine solubility at different temperatures. Use of curve to know the solubility at different temperatures. The question is as follows. Study the solubility of potassium chloride below and use it to answer questions that follow. So we want to draw a curve of the solubility of potassium chlorate. So this is y-axis, then we have x-axis. So we'll have that as our x-axis. Then we have what we call y-axis. So this is 20, 40, 60, 80, 100. Temperature in degrees Celsius. Then y-axis is solubility in grams per 100 grams of water, and that is 10, 20, 30, 40, 50, 60. So let's plot. We have 100, the first plot is 2510, then we have 60 to 30, then we have 154, then we also have 40, $17, 40 with 17. Let's try to join these points to have our solubility, then use it to answer the questions that follow. Good. So that is the solubility curve of potassium chlorate. Question: find the solubility of potassium chlorate at 90 degrees Celsius. So to answer that question, we get to 90 degrees Celsius, then we draw a line. So this is 90 degrees Celsius, where we have that straight line, and then against this side, that is 90 degrees Celsius. That gives a solubility of around 48 degrees Celsius. That is solubility of 48 grams per 100 grams of water. Good. B, a solution containing 30 grams of potassium chlorate per 100 grams of water was cooled to 25 degrees Celsius. A, Roman 1 will be Roman 1, at what temperature did the crystals appear? Let's first answer that question. First of all, we'll look at the solubility at 30 degrees Celsius. So it is 80, not 30, but 80 and 25. At 80 degrees Celsius, cooled to 25, then what temperature did the crystals appear? So first of all, 30 degrees Celsius gives 64. So that is 30 degrees Celsius. If you narrow down that to the line, so the answer is exactly 64 degrees Celsius. That is Roman 1. That is 64 degrees Celsius. Then what was Roman 2? What was the mass crystals obtained. So the mass of crystals obtained will work out some subtraction, which means we are going to read at 25 degrees Celsius and that 30 grams. So let us get the solubility at 25 degrees Celsius. The solubility at 25 degrees Celsius, exactly 10. So that is that 30 which was used minus 10. So that gives 30 grams minus the 10, giving 20 grams. Now, solubility at 25 is 10 grams. We are saying that the solution had 30 grams of the solute and therefore 20 grams of solute will crystallize. Solute crystallizes. So that is all about solubility curves. And remember, the first thing we just plotted the curve, then we generalized the way different salts have different curves, and finally we have used our curves to determine temperature and solubility. Let's talk about fractional crystallization. This is the process for separating soluble salts in a solution. It is sometimes called recrystallization. A salt such as sodium chloride can be contaminated with maybe small amount of a different salts. Another salt. That make it to be unfit for several uses such as consumption. The salt can be purified by fractional crystallization. In fractional crystallization, the contaminated salt is dissolved in water to make a saturated solution. The solution is heated to approximately 80 degrees Celsius. When it is cooled, crystals of the desired substance form, leaving the impurities in the solution. So these impurities remain in the solution because of two main reasons. One, they are more soluble. At higher temperature. And two, they are present in very small quantities. And cannot crystallize when the solution is cooled. Meaning they would only crystallize out if they were present in higher quantities. So we can therefore use this fractional crystallization to separate soluble substances. I want us to consider this. Let's say we have this as impure salt. Then we dissolve it in water to make a saturated solution. This is completely now a saturated solution. Pure salt crystallizes when we heat. Now on heating using water bath, pure salt crystallizes. Then simply this can be freezing mixture. Then filter that to obtain now pure salt. So that is how fractional crystallization is performed. It can be used to separate any soluble substance, more so if they have a wide range in solubility. That is all about fractional crystallization. About water hardness. As our last subtopic in the topic acids, bases, and salts. Hard water is one that do not or does not. Hard water is simply a water that does not form lather with soap. And this hard water contains magnesium ions and calcium ions. It contains magnesium ion and calcium ion. An example of hard water is the mineral drinking water, which has dissolved calcium ions and magnesium ions. That is in the form calcium hydrogen carbonate or magnesium hydrogen carbonate. So these ions react with soap. It contains magnesium and calcium ion, which react with soap to form insoluble substance called scum. It therefore says that hard water contains calcium ion and magnesium ion that are now the ions responsible for water hardness. Water hardness exists in two types. There is the first one, temporary water hardness. That is removed by boiling. Temporary, simply to remove that hardness is by boiling. Then we have the other type that is called permanent water hardness. Permanent water hardness. So permanent water hardness is the one that cannot be removed by boiling. So as the temporary water hardness are possible to be removed by boiling, it is not possible to remove a permanent water hardness by boiling. We have said that these ions form scum when they react with soap, meaning they do not end to formation of solution, but instead they give precipitates. What are the advantages of hard water? Advantages of hard water. Provides calcium, which is essential for strengthening bones. Another advantage, add water does not dissolve lead pipes. It does not dissolve lead pipes easily, since it has what is called a carbonate layer because of a carbonate layer. Or simply because of formation of a carbonate layer, therefore there is no contact, carbonate layer formation, therefore there is no contact between the water flowing in the pipes and lead. Remember, this magnesium and calcium ions, their carbonates are insoluble, so they will form a blockage, and that will prevent the contact between a water that is flowing and the lead. And lastly, this hard water is used for beer brewing. To brew beer, we use hard water. What are the disadvantages of hard water? It wastes soap. Hard water waste soap. We have said and repeated that this hard water does not readily lather with soap. So in the process, a lot of soap will be used, especially in the washings that involve hard water. Next, because it has some soluble ions, it stains white cloths due to scum formation. We have said it forms scum with soap, and because of that scum formation, it can end up staining the white cloth. Scum is simply a precipitate here. Another disadvantage is that deposition of calcium carbonate in kettles pipes and boilers. This reduces efficiency in boilers and may make hot water pipes to burst. You know, there is a kind of blockage. There is deposition of calcium carbonate. The calcium ions react with the carbonate ions to form the calcium carbonate, and this will deposit as you pass hard water through the pipes. It will deposit by forming an insoluble calcium carbonate, and that is what will eventually lead to bursting of hot water pipes. Is by boiling, and this only will remove temporary water hardness. So we have boiling that we've said removes temporary water hardness. During boiling, the calcium hydrogen carbonate and magnesium hydrogen carbonate decompose to form insoluble respective carbonates. For example, if we have calcium hydrogen carbonate that only exists in aqueous state, when that is boiled, that is boiling, it gives calcium carbonate, that is solid, plus carbon 4 oxide gas plus water. Now, this calcium carbonate form is in solid form, meaning it has no dissolved calcium ion, therefore no hardness, no water hardness. Similarly, when the magnesium hydrogen carbonate is boiling, it forms magnesium carbonate that has no dissolved magnesium ion plus carbon 4 oxide gas plus water. The second method of removing water hardness is addition of sodium hydrogen carbonate. B. Addition of sodium hydrogen carbonate. So when you add sodium hydrogen carbonate, the calcium ions and magnesium ions get precipitated, and this will remove both types. It removes both types of water hardness. So what happens? Sodium hydrogen carbonate is having sodium ions, carbonate ions. So the carbonate ions is what will react with the respective ions that bring the hardness, that is calcium ion and magnesium ion, and that will lead to formation of insoluble salts, i.e. magnesium carbonate and calcium carbonate. So this is what we are saying. Now, the calcium ion in the hard water will react with the carbonate ion. This is from sodium hydrogen carbonate, and that leads to formation of calcium carbonate that is insoluble. So this one has no dissolved calcium ion, hence no hardness. Similarly, magnesium ion reacts with the carbonate ion to form magnesium carbonate that exists in solid state, therefore has no dissolved magnesium ion. Another method of removing water hardness, that is part C, is distillation. This method removes both types of water hardness. And the distillation we are talking about here is simple distillation, where we are simply heating for dissolved ions to remain as a solute. Then we simply collect our solvent as a distillate. So during distillation, the solution or that water is heated, and during heating, the solvent part of that hard water, which is pure water, will escape in form of vapor and finally get condensed using Liebig condenser, and that gives the distillate, which is pure colorless liquid, and the dissolved ions will remain in the end where heating is taking place, that is in the round bottomed flask. So there is another way that we can use to remove both permanent and temporary water hardness. The last method to be used to remove water hardness is ion exchange. This means exchanging the hardness causing ions, that is magnesium and calcium, with sodium ions, which do not cause hardness. The materials used in ion exchange are called resins, and the resins are normally small beads that contain long molecules which bear the ions to be exchanged. Now, during that, we can have hard water in. So this is the ion exchange. So add water in. Then this consists of sodium ion, so after the exchange there will be soft water containing now sodium ions. Ion exchange calcium before add water is formed through. So this add water contains magnesium ion and calcium ion. So during the ion exchange, this ion exchange column before hard water is passed through. Then there is ion exchange column after passing hard water. Calcium ion that is now having calcium after exchanging the ions. So what passes out is soft water now containing sodium ions. So this is exchange column after hard water is passed through. So these are the ways that you can use to remove water hardness, and that is all about water hardness, where we have talked about permanent water hardness and temporary water hardness. But we can include some other methods as well, like addition, that is D. You can also talk about addition of calcium hydroxide. So in this process, a known amount of calcium hydroxide is added to water containing calcium hydrogen carbonate, and during that there is formation of calcium carbonate which is insoluble. So we'll have calcium hydrogen carbonate plus calcium hydroxide, and that gives calcium carbonate solid plus water. So after adding this calcium hydroxide, we are forming an insoluble salt that has no calcium ion. To balance the equation, we have 2 there and 2. Then that is liquid, that is aqueous, and our equation is balanced. Finally, we have addition of ammonia solution. Addition of ammonia solution. So ammonia solution, when added to water containing calcium hydrogen carbonate, again there is formation of calcium oxide, and this calcium carbonate, this calcium carbonate has no dissolved calcium ion. This method only removes temporary water hardness. And it is as follows the equation, that is calcium hydrogen carbonate reacting with ammonia solution, and that gives calcium carbonate solid plus water plus ammonium carbonate. That is aqueous. The equation is balanced by having 2 there. Then we have this as the solid, which has no calcium ion. Hence, the hardness has been removed. So now, after looking at the two additional methods of removing water hardness, that therefore marks the end of the topic acids, bases, and salts.